One of the unique things about the transition metals is the exceptions that they impose on our general rules and trends that we apply to the periodic table. And electron configurations are one of these areas. And so within our transition metals, we have exceptions to the rule set that we created for predicting the electron configuration of an element. And so I've got a list of these common exceptions that have been found experimentally. The ones that I feel we see the most are copper and chromium, which are in that first transition metal row. And we see that our copper promotes something from an electron from the s orbital into the d orbital to completely fill it. And our chromium does the same thing, but to half fill the d orbital. And so in that first row, we see this exception come up again and again for copper and chromium. And then moving down into the other periods of our periodic table, we see a few more exceptions occur. For molybdenum, we see that same prioritization of half filling our d orbitals, and we see a promotion from the s orbital into the d to half fill it. The next two are a little bit different though. And so these are lower on the periodic table. We're looking at ruthenium and palladium. And they're going to kind of bulk the trend because they're actually going to instead promote into something that won't half fill or fully fill with just one electron. So ruthenium has 6 d electrons, and it actually promotes one of its s electrons to fill it, so has 7 in the d orbital. So that's not half filled, it's not full, so it's a little bit harder to remember. And then palladium, we see has a 4d8 electron configuration, and so it actually takes both of the s electrons and promotes them into the d orbital to form 4d10 and to completely fill it. If you're going to keep any in your head at all, I strongly recommend keeping copper and chromium. I think those are our two most common exceptions here, and also the elements that you're probably most likely to run into, especially if you're looking at biologically relevant transition metals. All right, so let's talk a little bit more about why that 4s orbital is actually lower in energy than the 3d orbital, and we see these exceptions even occur. So here is a radial probability distribution for electron density within the atom, comparing specifically the 3d orbitals and the 4s orbitals. So when we're looking at our 3d orbitals, we have, and if you got to recall back from when you learned about this, which I know it was a minute ago, but our d orbitals all have 2 planar nodes in them, right? Which means that at the 3d level, that 3 represents n, our principal quantum number. The number of nodes that we'll have will be equal to n minus 1. So 3 minus 1 in this case, or 2. Well, both of those nodes are taken up as planar nodes. So we have 0 radial nodes. So we're going to, that means that there's no radial distribution of 0 electron density within that orbital. And so we can represent the probability of finding an electron relative to the nucleus with this single Gaussian curve right here that trails off. And that it's most probable to be here a little further away from the nucleus. If you look down, right, so the nucleus, the distance from the nucleus is right here is 0. There's pretty low probability of finding that d electron there in the beginning. Now, if we compare that to the 4s orbital, where again we have n minus 1 nodes, and so we're going to have 3 nodes. And s orbitals have a shape of just a sphere. They have 0 planar nodes in them. And so thinking about that, that means that all 3 of these nodes right here are radial nodes, which means there's kind of like a gobstopper. There's like a sphere of zero probability that the electron can be embedded within that orbital. And there's actually 3 of those spheres further and further out. And they're represented right here where that radial probability of electrons existing hits 0 again. And so those are our 3 radial nodes for our 4 S orbitals. And so that really kind of changes the probability of finding an electron close to the nucleus. Those radial nodes create this peak. And if you look at this right here, I'm going to get rid of everything around here. This area right here by the nucleus closest, you can see that there is actually a greater probability of finding that 4s electron near the nucleus than the 4d electron. And so that's going to lower its energy. It has a better penetration in towards the nucleus. So it's going to feel more of that positive, negative electrostatic attraction that kind of holds this whole thing together. And it lowers the energy of those 4s orbitals. It lowers them below the 3d orbitals. And so that's why we fill the 4s orbitals first with an electron, because it's stabilized by that greater interaction with the nucleus. And it's why we see a close energy in between those 3d and the 4s. And so that energy difference between them is pretty small.